The tensile test.
May audio.
First test, material with yield.
Okay, good.
The tensile test. First test, material with yield point phenomenon. In the first tensile test, a plain carbon steel with yield point phenomenon is to be tested. This is the test piece. It has a cylindrical test region with an original diameter of 10 mm and an original gauge length of 100 mm. Within this test region, distance marks have been drawn at regular intervals. They help to visualize and measure the plastic behavior of the specimen. Using a hand control, the tester moves the upper crosshead into its correct starting position. Now he can place the threaded ends of the test piece in the lower and upper grips of the testing machine. In the next step, he swings the extensometer into its working position and checks that everything is correctly prepared. Then he selects all necessary testing parameters on the control computer. Ready. The test starts and the extensometer's sensor arms are carefully pressed onto the test piece. This way, the gauge length can be measured throughout the whole tensile test. The gauge length is displayed at the bottom right-hand corner of the screen. At the beginning, it amounts to 100 mm. During the tensile test, the test piece is slowly and constantly elongated with a standardized speed. The force that the test piece opposes to the imposed elongation is recorded and can be seen at the bottom left-hand corner of the computer display. The material behavior can best be observed in a force elongation diagram. The force F is being plotted upwards on the vertical axis, the elongation delta L towards the right on the horizontal axis. At first, the force rises rapidly. Force and elongation are proportional and form a steep, straight line in the diagram. In this area, the material behaves elastically. If the test piece were to be unloaded from this area, it would spring back completely to its original length. In materials with yield point phenomenon, the end of the elastic area can be seen clearly. The plastic deformation starts abruptly and is accompanied by a sudden drop of force. If the test piece were to be unloaded now, it would not spring back to the original length, but instead show a permanent elongation. In the next stage of the tensile test, an almost constant force level with slight fluctuations occurs. This phenomenon is called the Luders effect. After a certain strain, known as the Luders strain, the force increases again. The material opposes an increasing force against the imposed elongation. It strain hardens. Up to the point of maximum force, the test piece is strained uniformly along its length. This means that the test piece gets longer and thinner, but keeps a cylindrical shape. As soon as the maximum force is reached, a neck begins to form at one point of the test piece. All further plastic deformation now only takes place at the neck, and eventually the test piece fractures there. In the recorded force elongation diagram, the force FEH at the upper yield point can clearly be seen. This is the highest force the test piece can sustain elastically. FEL is defined as the force at the lower yield point, Fmax as the maximum force. Using these forces, the strength properties of materials can be calculated. The upper yield strength REH is calculated by dividing the force FEH by the original cross-sectional area S0. The lower yield strength REL is defined in a similar way. The maximum force divided by the original cross-sectional area is called tensile strength Rm. In the last step, the tester swings the extensometer back into its resting position and removes the broken test piece. On the work table, he puts the fragments back together again. With the help of the distance marks, the percentage elongation after fracture can be determined. This is the permanent strain after fracture and amounts to about 30% in this example. Please note that the percentage elongation after fracture depends on the length to diameter ratio. By measuring the smallest diameter at the point of fracture, the percentage reduction of area can be calculated. It describes the reduction of cross-sectional area at the point of fracture in relation to the original cross-sectional area. In the second tensile test, a material without yield point phenomenon is to be tested. In this case, it is a precipitation-strengthened aluminium alloy. The test piece has exactly the same shape and dimensions as the specimen in the first test. It is cylindrical, with an original diameter of 10 mm and an original gauge length of 100 mm. After fitting the test piece into the testing machine and panning the extensometer into its working position, the test can start. The initial linear curve in the force elongation diagram again shows the elastic behavior of the material. But this time, the end of the elastic area is not revealed by a sudden drop of force or any distinct change. There is a smooth and gradual transition from linear elastic behavior to plastic deformation. In the further course of the tensile test, the force increases and the test piece again is strained uniformly along its length. At the point of maximum force, a neck develops, and all subsequent plastic deformation is confined to this neck until fracture finally occurs there. As a common substitute for the yield strength, the 0.2% proof strength is used. It is the stress that causes 0.2% of plastic deformation in the material. And this is the way to calculate it. First of all, the elongation that corresponds to 0.2% of strain has to be computed. For an initial gauge length of 100 mm, the result is 0.2 mm. In the force elongation diagram, a straight line parallel to the elastic line is drawn through the offset point of 0.2 mm of elongation. The force at the intersection point of the offset line with the force elongation diagram is designated as Fp 0.2. This is the force that causes a plastic strain of 0.2%. The 0.2% proof strength, Rp 0.2, is equal to Fp 0.2 divided by the original cross-sectional area S0. Tensile strength, percentage elongation after fracture, and percentage reduction of area are calculated in the same way as in the first test.
Okay, so the next two videos will define the different material testing. Okay, so for the classifications of this material testing, we have the two major types, which we call the destructive testing and non-destructive testing. Okay, so under destructive testing po, yung gagawin natin na yung ginawa natin na hardness test, same thing with yung bukas na tensile test, okay? And then see difference between the two. So you take note the difference between DT and the NDT method, okay?
Lala to wala with Medical Advance 400.
Welcome to this video on destructive testing versus non-destructive testing. When testing products or materials, there are two broad categories of tests: destructive testing and non-destructive testing. In this video, we will discuss the basic differences between the two, their pros and cons, and some of the methods used in each category. What is destructive testing? Let's begin with destructive testing. As the name suggests, destructive testing is a type of testing that involves damaging or destroying the product or material being tested to observe its behavior under extreme conditions. This type of testing is often used to understand the limits of a material's strength, durability, and other mechanical properties. Destructive testing is typically conducted on a sample or prototype of the product or material. The sample is subjected to a load, pressure, or other extreme conditions until it fails. The data collected during this process is then used to determine the material's strength, elasticity, and other properties. Some of the most common destructive testing methods include tensile testing, compression testing, bend test, macro test, impact testing, fatigue testing, and hardness testing. Tensile testing involves applying a force to a sample until it breaks, while compression testing involves applying pressure to the sample until it deforms or fails. Impact testing is used to measure the toughness of a material by striking it with a weighted pendulum. Hardness testing measures the resistance of a material to deformation. While destructive testing provides accurate data on a material's properties, it is not without its drawbacks. Since it destroys the sample, it is often not practical for use on expensive or rare materials. Additionally, destructive testing can only be conducted once, making it difficult to retest materials. What is non-destructive testing? Now let's move on to non-destructive testing. Non-destructive testing is a type of testing that does not damage or destroy the product or material being tested. Instead, it uses various techniques to observe the behavior of the material without causing damage. Non-destructive testing is often used to evaluate the integrity of a product or material, detect defects or flaws, and ensure that it meets quality standards. Some of the most common non-destructive testing methods include ultrasonic testing, radiographic testing, magnetic particle testing, and visual inspection. Ultrasonic testing uses high-frequency sound waves to detect defects in a material. Radiographic testing uses X-rays or gamma rays to produce images of the internal structure of a material. Magnetic particle testing is used to detect surface or near-surface defects in ferromagnetic materials, and visual inspection involves visually examining a material for any defects or flaws. Non-destructive testing is generally less expensive than destructive testing and can be used on expensive or rare materials without damaging them. Additionally, non-destructive testing can be conducted multiple times, making it easier to retest materials and track changes over time. In conclusion, both destructive testing and non-destructive testing have their advantages and disadvantages. Destructive testing provides accurate data on a material's properties but destroys the sample. Non-destructive testing, on the other hand, can be used on expensive or rare materials without damaging them but may not provide as much accurate data as destructive testing. When deciding which type of testing to use, it is essential to consider the material being tested, the desired outcome, and the available resources. By choosing the right type of testing, you can ensure that your products and materials meet the highest quality standards.
Lunod sa requirements. Mentos muna!
Welding visual testing. What you need to know.
Destructive and non-destructive testing. Through this lesson, you will be able to understand various types of destructive and non-destructive testing. Also, we will discuss the comparison between them with various examples. Before we discuss non-destructive testing and destructive testing, let us summarize why we need to test a material before we using it for a purpose. Material testing is to determine service life and to detect design weakness that may not show up under normal working conditions. Data collected through these tests is highly important to take vital decisions in various stages of product manufacturing. Material testing also plays a large role in failure analysis investigation to help and identify defective parts. Material testing can be broadly classified into two: destructive testing and non-destructive testing. As the name indicates, destructive testing will changes the dimension or physical and structural integrity of specimen in order to identify its capabilities. But in case of non-destructive testing, measurement will not affect the specimen or it will not make any changes over the physical or chemical properties of the material. Now let us discuss the peculiarities of destructive testing. Destructive testing is undertaken in order to understand a specimen's performance or material behavior. These procedures are carried out to the specimen's failure. Destructive testing procedures can either follow specific standard or can be tailored to reproduce preset service condition. It also destroys or changes the part in some way or other such that even if it is passes the test, it is no longer fit for the service. Hence, this kind of test is not economical for relatively small scale manufacturing. However, destructive testing is recommended for mass production. Now let us discuss some examples of destructive testing. Tensile and compression tests are most commonly used destructive testing method in industry. The evaluation of mechanical behavior of sample under conditions of tension and compression can be performed to provide basic material property data that is critical for component design and service performance assessment. Testing can be performed on a mechanical material sample or a full-sized or scaled models of actual components. These tests are typically performed using a universal mechanical testing instrument. A tensile test is a method for determining behavior of material under axial tensile loading, while a compression test is a method for determining the behavior of material under compressive loading. Most of the time, we can use universal testing machine to perform both compressive and tensile tests. Hardness test is another kind of destructive test that we usually perform to evaluate a material property, such as strength, ductility, wear resistance, and also help us to determine whether a material or material treatment is suitable for the purpose we required. There is many methods are available in industry, but the popular methods are Brinell hardness test, Rockwell hardness test, and Vickers hardness test. In general, different materials differ in hardness. For example, hard metals such as titanium, beryllium are harder than soft metals such as sodium and metallic tin, or wood and common plastic. These instruments help engineers to choose a material based on its hardness. Pendulum impact tests are carried out to identify material's ability to resist impact force. Or other words, it will give an idea about toughness of material. Toughness or resistance of a material to tearing is related to energy absorbed by the part during the fracture. Charpy impact test, one of the popular method in industry to measure toughness of material. Similarly, we can use Izod impact test for same purpose. In these methods, the pendulum is released and specimen is broken within a fraction of seconds due to high impact from swaying pendulum. Hence, the name destructive testing. Now let us discuss non-destructive testing. Non-destructive testing, or NDT, is the process of inspecting, testing, or evaluating materials, components, or assemblies for discontinuities or differences in characteristic without destroying the serviceability of the part or the system. In other words, when the inspection or test is completed, the part can still be used. The most commonly NDT techniques are eddy current method, magnetic particle test, liquid penetrate method, radiographic technique, and ultrasonic testing. There is many other examples are out there, but in this lesson we will focus the popular ones. Eddy current test is based on the physics phenomenon of electromagnetic induction. In an eddy current probe, an alternating current flows through the wire coil and generates an oscillating magnetic field. If probe and its magnetic field are brought close to conductive material like a metal test piece, a circular flow of electrons known as eddy current will begin to move through the metal, like swirling water in a stream. That eddy current flowing through the metal will in turn generate its own magnetic field, which will interact with the coil and its field through mutual inductance. Changes in metal thickness or defects like near surface cracking will interrupt or alter the amplitude and pattern of eddy current and resulting magnetic field. This in turn affects the movement of electrons in coil by varying electromagnetic impedance of coil. The eddy current instrument plots changes in the impedance amplitude and phase angle, which can be used by a trained operator to identify changes in the test piece. Magnetic particle testing is a non-destructive inspection method that provides detection of linear flows located at or near the surface of ferromagnetic materials. It is viewed primarily as a surface examination method. Magnetic particle inspection is very effective methods for locating surface breaking, slight subsurface defects such as cracking, porous, cold lack of sidewall fusion in weld. This testing is limited to magnetic material. Materials such as wood or plastic will not react with this device. Liquid penetrate testing. Liquid penetrate testing is one of the oldest and simplest NDT method, where its earliest version dates back to 19th century. This method is used to reveal surface discontinuities by bleed out a colored fluorescent dye from the flow. The technique is based on the ability of a liquid to be drawn into a clean surface discontinuity by capillary action. After a period of time called dwell time, excess surface penetrant is removed and developer applied. This acts as a blotter that draws the penetrant from the discontinuity to reveal its presence. So by using this technique, we can easily find out minute cracks on the surface. Radiographic testing is a non-destructive testing method which uses either X-rays or gamma rays to examine internal structure of manufactured components and identify any flaws or defects. In radiography testing, the test part is placed between the radiation source and film. The material density and thickness differences of test part will influence the penetration radiation through interaction process involving scattering and absorption. The differences in absorptions are then recorded on film or through an electronic means. Ultrasonic testing is yet another technique in NDT which uses a piezoelectric transducer connected to flow detector, which in its most basic form is a pulsar receiver and oscilloscope display. The transducer is passed over the object being inspected, which is typically coupled to test object by a gel or oil, or maybe sometimes we could use the water as well. The signal received from transducer can be analyzed with the help of a computer interface. As a non-destructive testing method, ultrasonic testing is ideal for detecting flaws and defects without damaging object or material being tested. Periodic ultrasonic inspection can be used to check for corrosion, for growth of non-flows and thus potentially prevent the failure of part. It is used in a wide range of industries including aerospace, automotive, construction, medical, metallurgy and manufacturing. Now let us discuss the difference between destructive testing and non-destructive testing based on few parameters. If you take the purpose of these kind of testing, the destructive testing carried out to find the properties and behavior of specimen under different loading conditions. At the same time, non-destructive testing is used to find properties of a material and to find out its defects. Here, the more focus is on finding the defects of that material rather its ability to carry loads. If we think about the specimen that we use for this kind of testing, whenever we carried out destructive testings, the specimen will damage and hence the name destructive testing. But at the same time, the non-destructive testing or NDT will never damage the specimen. Hence it is very useful for small scale manufacturing. And goes to the third parameter, defects, and we know that defects cannot be found using destructive testing because it's only give you the idea about how much load it will carry or how much force it can withstand. At the same time, NDT will help you to identify minute microstructural defects in the material. And the cost involvement for these two types of testing, since it is destroying the material, it is obvious the destructive testing is more costly and the equipment for the testing requires a high initial investment as well. But in case of non-destructive testing, the cost is comparatively less because we can reuse the test specimen. These are some more examples of destructive and non-destructive testing. The tests such as bending test, tensile test, compression testing, and impact testing are destructive, while ultrasonic testing, liquid dye penetrate method, eddy current testings belongs to non-destructive testing.
Hi, I'm Edon, and I'm a community manager here at StoreHub. Alam namin that managing an F&B business.
The tensile test. First,
Okay, so you have seen there a video pertaining to the difference between the destructive testing and that of an NDT. So, yun pong dalawa nating experiment na nagawa that falls under destructive testing. Okay? So, and then another one, yung pong by next week, that would be another form pa rin po ng destructive testing. Okay? So, dito po sa university kasi, wala tayong masyado equipment for the NDT. But then, if it is grounded, okay, it is an area to which we can focus on. Okay? So, as a mechanical engineer, pag nakatapos kayo, maganda din na mag-venture kayo onto this NDT. Okay? So, there are a lot of opportunities, job opportunities dealing with this NDT thing. Okay? So, iyan po. So, ano basically yung difference ng dalawa? Pag sinabi po natin na destructive testing, okay, so, ang ginagawa natin sa material is we put that into dinidestroy talaga natin siya, sinisira natin siya for us to be able to determine its properties. So, extreme conditions yung ina-apply natin sa kanya. Kasi, if we will be using only the normal conditions, so hindi po natin makikita yung kanyang failure. Okay, and we are not able to determine yung kanyang mga properties. Okay, pero pag sinabi naman po natin na NDT, okay, this is merely inspection without doing harm. Okay, that's the simplest definition of it. Okay, that is doing inspection, okay, without doing harm on the material. Okay, or conducting inspection without doing harm on the material. Okay, so most specifically, parang anong ginagawa natin dyan? More on the prevention side tayo. Okay, we deal with the cracks or any other surface discontinuity para maagapan yung totally na pagkasira ng material. Okay? Nakuha po ba? Nakita ba yung difference ng dalawa? And some are other differences as summarized po doon sa huli. Okay? So, iyan lang muna po for today. And then, may question po ba ang anyone? Hello? Wala. Okay. So, tomorrow po, okay, I expect you to be here po for our experiment. And then, ilalagay ko na lang din po today, okay, yun po ang ating magiging template, okay, for the experiment po tomorrow. Kindly see na lang po yung template and then by group, you convene and then tingnan po natin kung alin na yung pwede nating malamnan, okay, doon sa atin pong template na yun. Okay, of course there are those literatures that needs to be put doon sa or included doon sa atin po na template. Okay, so you can convene by group para po magawa po natin. Okay, so kung wala na po tayong question, okay, I'll pa-open na lang po ako ng ating camera saglit, although mahina yung connection din sa university ngayon. Okay.